Assalamu alaikum. This is a first of 4 lectures on laser microlaryngosurgery. This first lecture is on the principles of the use of laser in microsurgery of the larynx. When laser is used in the management of vocal fold nodules or polyps, or in microlaryngosurgery in general, the surgeon would have to select and choose between different types of lasers and also different systems of delivering the laser. The output of the energy can be in various ways, either continuous or interrupted like pulse, and the amount of energy used in the type would depend on the type of surgery required. He will also have to decide and set up the machine whether he needs the focal spot to be a point or a line or a circle, and the dimensions of this spot, and whether it is straight or curvilinear like here, and the depth of penetration in the very delicate epithelium of the vocal folds. And also he would have to decide if he is using a pulsed energy on the time in which the energy is pulsed on to deliver the amount of energy required for cutting or ablation, and also the time in which the pulse is off to allow for the cooling of the tissues. In the next 4 lectures, we shall be going through things like the principles of the use of laser in microlaryngosurgery, and then a lecture on the safety and the anesthesia consideration in this type of operations, a third lecture on the use of laser in phonosurgery for benign vocal fold lesions, and the fourth for the use of lasers in the management of early malignant lesions. In this very first lecture on the principles of laser microlaryngosurgery, we'll be covering the basis that of the different factors that would help the surgeon decide on what type of laser, which system, the energy, the pulse, the mode of delivery of the system, things starting from the very basic issues like the 3 key components of the laser and the 4 fundamental characteristics of a laser beam, the laser wavelength of different mediums relative to the absorption coefficient of different types of tissues. We'll also be covering things like the adjustable parameters of the laser machine, including the choice of the required energy in joules and the amount of power delivered and the irradiance. We'll also be discussing fluence and the power density and the threshold of energy required for ablating or cutting into tissues. We'll be discussing thermal relaxation time required for tissues to cool down, and also the duration of the pulses of the laser energy, the size and the shape of the focus beam, and the penetration depth, and finally the output pattern of the laser beam. The 3 key components of laser are first a lasing medium. This can be, for example, carbon dioxide or any of these mediums, KTP or other material. This medium will be excited by pumping energy through a lasing, so an excitation source. This can be an alternating electric current, for example. The excited lasing medium will be contained into a specially designed chamber with mirrors at the 2 ends of the chamber. One of them would be partially reflective and partially refractive, allowing some but not all of the light to pass through. Now, exciting the lasing medium in here by pumping energy would release electrons, which in turn could start a chain of reactions, ending by the release of packets of energy from atoms of the medium in the form of photons. And these photons will reverberate between the 2 mirrors at the ends, and each time they reverberate again, they release more photons from other atoms until most of the medium is in the excited state, and this will produce enough photons. Some of them would pass through the one of the mirrors in the form of laser energy. This summarizes the chain of reactions after exciting the lasing material within the chamber. The population of, say, carbon dioxide atoms will be excited, and when enough of them are excited, something called population inversion would happen when most of the atoms are in the excitable state and can emit photons. And the beam is amplified by reverberating between the two mirrors, and they keep on stimulating other atoms to emit photons, and finally some of these photons will be released from one of the mirrors at the end in the form of a beam of laser. And this beam of laser has four fundamental characteristics that are different from ordinary light, for example, and that they are extremely intense. They are very brilliant. The beam is very brilliant compared to the normal light. And the beam is also coherent in that the photons in the beam travel in phase, vibrate in phase, both in space and in time with each other, and this would allow for an extremely narrow beam. This narrow beam can be focused into a very small spot. This is high collimation. And finally, it's monochromatic in that all the photons have, all the emitted light has only one wavelength. So they have only one wavelength in the spectrum. These are the four fundamental characters of the laser beam. Now, when the laser beam is directed to certain tissues, it can be, the energy in it would be absorbed by special chromophobes, certain molecules in the target tissue that can absorb the energy preferentially, like for example hemoglobin or water or melanin tissues and cells. And preferably the other parts of the tissues would not absorb enough energy so that no collateral damage is going to happen. Now, the maximum absorption of the energy would occur when the wavelength of the lasing beam is identical or matches the absorption coefficient of the chromophobe. Like certain chromophobes, for example, the oxyhemoglobin has a peak absorption coefficient between 542 and 577 nanometers, and when it is hit by a wavelength of phase of laser, for example a KTP, which have also a peak at this area, a preferential absorption by hemoglobin would occur. Something similar would happen with carbon dioxide and water. The absorption of the water would peak of above 10,000 nanometer, and this is around the wavelength of the carbon dioxide laser. So this would give preferential absorption either to hemoglobin in the case of KTP or of water molecules in the case of carbon dioxide. And this would summarize the different laser types, including carbon dioxide and KTP and dye laser and DIAG, who have different wavelength. Carbon dioxide would have a very long wavelength above 10,000, and the others would have a much smaller wavelength. The chromophobe that would preferentially absorb the energy from carbon dioxide would be the water molecule in the soft tissues of the target larynx, for example, whereas in KTP and the others, it would be selectively absorbed by hemoglobin, oxyhemoglobin in blood vessels. And this would lead, in the case of carbon dioxide, to vaporization of the water that can cause tissue ablation or incision. So it can be used to cut into the vocal fold tissues or ablate things like papillomas. whereas the others with a much lower wavelength, the energy would be used and hit the hemoglobin and cause coagulation or selective coagulation in blood vessels, and sometimes it can be helpful also in the recurrent papillomatosis within the ND-YAG, for example. So the KTP can manage things like hemangiomas or vascular lesions, plus the recurrent papillomatosis. So that's one aspect of the laser energy, the wavelength, and this cannot be adjusted. You can only choose between different types and select the most appropriate for the job. But there are other parameters that can be adjusted, and it's the laser power in contrast to the wavelength, which you can only be selected, and the appropriate one will be selected. You can actually adjust the amount of energy produced by the lasing machine, and you can also adjust the size and the shape of the focus beam, the spot the lasing beam is going to hit, and there are no single best set of adjustable parameters. You would choose different parameters to effect the best possible outcome for your job. But this is the adjustable parameter of the laser. So while discussing the adjustable parameter of laser energy, we should be referring to 4 different ways to measure the laser energy. The first is the total energy in joules. This is related to the number of photons in the stream of the beam. This is the total amount of energy produced by the beam itself. But what is more important is the power, which is the energy divided by the time. It's the number of photons streamed in a second. This is another way of referring to the energy rather than the total energy. The rate of delivering of the energy is the power. And then there is the irradiance, which is the power divided by the surface area of the target tissue. This is basically the density of the energy distributed over a certain area. So it's the power divided by the area. And finally, this is the most important way of describing the laser power, is the fluence, which is the irradiance multiplied by time. This is the amount of power, the rate of delivering of the energy divided by the surface area of the target multiplied by time, the total amount that actually hits the target. So this is the dose of the energy delivered to the target tissue, the fluence. So far we have been through the energy, the adjustable energy required for a certain surgical task, and here the total energy required is 10 watts, and that should be distributed over a certain area and also over time. The area can be determined by the surgeon as well, and he may choose a straight or a curved line with a certain length, 1 or 2 millimeters more or less, and also a depth, which can be something like, again, a fraction of a millimeter or more. But there is this other aspect now, the time through which this energy would be distributed over this focus area. Not only the time when the energy is on, which should be very brief, but also the time when the energy is off to allow for the cooling of the tissues to avoid charring. And this we're going to discuss over the next few slides. This time off and time on would be dependent on something called the thermal relaxation time of the tissues. This is the time taken by the tissue temperature to drop to 50% of the initial temperature, and this will decide the time on and the time off, as we will see in the next few slides. This diagram would show the variation of the temperature of the target tissue on the y-axis with time on the x-axis. The effect of the energy in the laser beam in heating up the tissues would be resembled in here. Now, for every type of tissue, there is a certain target temperature. In, for example, the water, the target temperature would be close to 100 degrees centigrade. So you need to reach a temperature of 100 degrees centigrade to cause vaporization of the water and destruction of the tissue. But you need to get this temperature rise very quickly, because if the rise in the temperature is actually slow, like in the longer pulse here, the tissues would start to cool down related to its thermal relaxation time and lose 50% of its energy over that specific time. So you need to get to the target temperature of the tissue, 100 degrees in a short pulse, peaked pulse, and this would cause a tissue destruction. If it is the rise of the temperature is slow by a long pulse, then the tissues would start to lose the temperature very quickly, and you may never achieve the target temperature of 100 degrees centigrade, or you would only achieve it for a very short while. The message here is that the thermal relaxation time would determine the pulse duration. Thermal relaxation time for water, or in carbon dioxide laser, for example, it's 0.8 milliseconds, less than 1 millisecond. The tissues would lose 50% of the heat. So the energy required to vaporize the water would have to be shorter in duration than this 0.8 milliseconds. You need a fast rising short pulse, like in this curve in here, shorter than the tissue relaxation time, and here the heat would remain confined during this very short period, give precise action and minimal collateral damage from the dissipation of the energy. On the other hand, if you have a longer pulse, which does not peak up quickly and does not peak up high, the slower rise would allow the heat to be spread to the adjacent tissue, and the threshold temperature required for tissue destruction may not be achieved due to the quick cooling effect, the very short thermal relaxation time. The energy delivered by the laser machine need to be focused in a spot in order to achieve the temperature required to ablate or cut into the tissue, and achieve this very quickly. Now this can be done through a lens in the end of the laser machine that focuses all the beam of the laser into a very tiny spot. This tiny spot can have dimensions of usually 0.2 millimeter up to 2 millimeters in the usual circumstances, but this can go up to 5 centimeters sometime. The idea is to have the amount of energy in a very focused way. This will give a precise cutting or ablation, and also will minimize the collateral damage to the surrounding tissue. Now, sometimes you would actually want the beam not to be too focused. Say if you have a little bit of bleeding or oozing from the tissues in here, you may choose to defocus the laser machine, so to become the end spot will be out of focus, and the energy would be distributed into a wider area, but at a smaller concentration, smaller density, and this could be helpful in achieving hemostasis for oozing areas or raw area. This can be useful for small vessels up to 1 millimeter in diameter. Larger vessels would need other arrangements like endoscopic clipping or cautery. When the surgeon selects a certain size for the incision or the ablation area, say a millimeter or two, the machine will deliver a focused beam over 1 or 2 millimeters according to the surgeon's desire. But when the surgeon chooses a penetration depth, something different would need to be done. The software of the machine would have to take into account the average energy absorption of that target tissue stored in the software, and accordingly calculates the amount of energy needed to achieve that depth. So it's not just that the surgeon would require something and the machine is going to deliver it, like the length. Here the machine would have to recalculate the amount of energy needed to achieve the depth. The system, when we select the incision depth, would now be allowed to vary the laser power to achieve that particular depth. The actual depth may depend on a variety of other factors, like if the wound is wet from bleeding or from other tissues or contains other chromophobes, but the calculated depth will be carried out by the software of the machine. So far we have been through how the surgeon would choose a certain amount of energy or power, and also specify a length of the cut and suggest a certain depth and the time on and the time off. But there are other aspects, other adjustable parameters that the surgeon would have to specify, and this is how the power pattern, the output pattern, would be. It can be continuous, like continuous flow of energy through the laser machine, or it can be pulsed, intermittent pulses of the energy. And these pulses can sometimes be very rapid, less than 1 millisecond, like the ultra pulse or the super pulse mode. The aim is to produce the desired effect of cutting or coagulation with adequate hemostasis of the small vessels and limited char formation. The earlier laser machines used a continuous flow of a lasing beam, a continuous wave mode of carbon dioxide laser beams, for example. But this mode caused significant collateral thermal damage surrounding the focused area, the incision or the ablation area. This is because the continuous mode would provide lower power and a long duration of pulsing, and this would result in wide and uncontrolled zone of collateral damage. This is why its use in phonosurgery has almost been stopped. And this is why surgeons had directed their attentions to the newer developments of super pulse and ultra pulse modes of laser operation. This chart would show the variation in the tissue temperature with time in the x-axis, and 3 different modes of delivering the laser. Now the target here is to achieve a certain threshold temperature, 100 degrees for example in the case of use of carbon dioxide, within a very short period of time, which is the thermal relaxation time of 0.8 milliseconds. And when the continuous mode is used, this is the dark blue in here, the ablation threshold of 100 degrees is not reached, and the 0.8 milliseconds required, so a lot of the energy would be dissipated and cause maximum collateral damage and charring. Whereas if the other 2 modes, the super pulse and in here, like the cones in here, and the ultra pulse, like the rectangles, would behave differently. They can achieve higher temperature in a much shorter period of time, shorter than the thermal relaxation time of 0.8 milliseconds, and therefore achieve a better and precise cutting and avoids the collateral damage. You could see that the ultra mode, the rectangle, would reach the required temperature very quickly, like a sharp vertical increase in the temperature, stays there most of the time before it stops the pulse, and the temperature would drop with the cooling of the tissues. The super pulse would have a cone-shaped curve. It would rise to the required temperature, but only after a bit of time, and would also stay there for a shorter period compared to the ultra pulse, and then the temperature would drop. So the chart would show that the super pulse would still reach the required temperature, but the rising and the fall is a bit long compared to the ultra pulse, which rises instantaneously and drops very quickly. In practice, both modes, the super pulse and the ultra pulse, have very similar outcome. The differences is very subtle, and it's perceptible only during surgery, but in the healing and the post-operative period, the vocal fold vibrations are basically similar with the two modes. You can argue that the clinical outcomes are equivalent, although the incisions carried out by the ultra pulse are marginally finer than the super pulse. Not all the energy delivered by the laser beam will be absorbed by the chromophobe, the molecule that is the target of the beam. Some of the energy will be reflected out of the surface, and this will be effectively lost for the surgical purposes and can cause unwanted thermal injury to adjacent tissues and sometimes also adjacent individuals. Other parts of the energy beam will be transmitted or scattered in the tissues, and this will depend very much on the physical properties of the tissues itself and the wavelength of the beam. Wavelength of the beam that are quite long, like the carbon dioxide, would have minimal scattering. The shorter the wavelength of the beam, the more scattering would occur. So after some energy is reflected, some other energy is scattered, and some energy is transmitted. Only a part of the energy will be absorbed by the chromophobe to effect the thermal damage required. And this is the only part of the energy that is actually of surgical benefit. One of the reasons why carbon dioxide laser is more popular than other brands of laser is that it has a fairly relatively long wavelength. This wavelength is in the infrared part of the spectrum. It's therefore invisible in the infrared part of the spectrum, but by combining it with a coaxial other aiming beam, the beam can be traced. The carbon dioxide also has a high coefficient of absorption by water, which is present in all living tissues, and that's why this is the chromophobe of the carbon dioxide laser. It will be absorbed preferentially by water molecules, and this action is independent of the tissue color. One further development of the carbon dioxide laser machine was the addition of the AccuBlade scanner system. This is a computerized mechanism attached to the micro manipulator of the laser machine and depends on mirrors that are oriented into the Y and the X axis that can be used to shape the beam into either a straight line or a curved line of varying lengths and penetration depth. The beam can be shaped into a very tiny, smallest possible diameter, in some cases down to about 1/4 of a millimeter. The number one in the AccuBlade scanner system is 250 micrometer, which is 1/4 of a millimeter, and number two is double that, this for a focal length of 400 millimeter, which is the usual in microlaryngosurgery. This new development allows a laser beam to scan a given target surface with extreme rapidity. This beam that scans the surface is referred to as the AccuBlade. And this AccuBlade scanner software would modify the laser beam, the ultimate laser beam delivered, to travel either a straight or a curved line with a certain length and a certain penetration power, and the incision can be rotated if it is curved either to the right or to the left using the joystick. So this AccuBlade scanning technology, when coupled with a super pulse energy delivery, can produce a very fine laser beam with specified length and adjustable penetration depth. It can also ablate tissue rather than incise it with a certain diameter and a certain depth as well, and the beam can either be straight or can be curved to the right or curved to the left, allowing a very precise cutting and minimal collateral damage. So combining the scanning AccuBlade with a super pulse mod would allow minimum heat dissipation and a greater power in terms of watts to be concentrated into a cutting of the tissues or ablating it. This would cause minimal char formation, and also the machine can calculate the optimal time on and off and recommend the power required to carry out the job. Each machine would have its own predetermined optimal fluence delivery. Variations in the settings can take place from one case to the other according to the surgical task, but the combination of the AccuBlade and the super pulse or the ultra pulse mods are probably the best used for the benign vocal fold lesions. By this we come to the end of this first lecture on the principles of laser microlaryngosurgery. Assalamu alaikum.